Good afternoon, all of you.
Good afternoon, sir.
Yeah, good
Good
afternoon.
afternoon, sir.
Good afternoon, sir.
Afternoon. Afternoon. Okay, so shall we start?
Yes, sir.
Great. So I guess you guys have a calculator and pen with you. We want to start some calculation. So we can do that, right?
Yes, sir.
Yes, sir.
Great. So I'll just share the screen with you. Hope you guys can see my screen. Yeah. So let us start doing this calculation in Excel sheet. That will be better. Okay. So what we want to do today is to calculate thickness for a cylinder. Okay. We want to find a thickness for a cylindrical object. What is the load for which we want to find the thickness? Right now we are discussing pressure vessel. So pressure is the main loading. So pressure will be required as an input to us, right? So what is the pressure? What is the pressure you want to consider? We are just example we are taking, so we can take any value. Okay, let us take 20 bar. Okay. Diameter. Guys. Any value if you want me to mention. So when I say diameter, you should ask whether I'm talking about inside diameter, outside diameter, or nominal diameter. So let's be very specific. We'll write it down as an inside diameter. I'll write it as DI. The value we will take as, let us say, 2.5 meters, so 2500 mm. Right? What else do we need, guys?
Material.
Material. So what material we want to take? Let us take a carbon steel. Okay. What specific grade? We are talking about material. So see, in pressure vessel, only CS is not sufficient, like carbon steel is not sufficient. We need to mention the exact grade of the material. Okay. Once we have that grade, we can find all the property related to it. Okay, that is the reason we want the material. Okay. So in this case, we are taking 516 grade 70. What else? Any other value I need for design? Apart from Hitesh, anybody like to tell?
Permissible stress.
Permissible stress. So what we call that value in design? What is the terminology which we use? Is allowable stress. Okay. So we call it as allowable stress. So we'll define this by S. How I can find the allowable stress for 516 grade 70?
So from the material given.
From the
stress strain diagram.
Yeah. So which code I need to refer? Whether I can find that in section 8 division 1. Section 8 division is 1 is what we are following right now, right? So where I will find the properties of material, in which section of ASME? Anyone?
Section 2.
Yes, absolutely right. And that was, who replied?
Sir Keshav.
Keshav. Good, Keshav. So allowable stress we will be getting from ASME section 2, which talks about material. Okay, I'll just open that and we are going to find out the property. Okay. So I'm opening section 2 part D. Okay. Now if you see this section 2 part D, there are different subparts to this. Subpart 1, which talks about stress table. Subpart 2, which talks about physical properties. What are the physical properties, guys? Any one of it you can name? Like,
Permeability, ductility.
yes, ductility, in density of a material, modulus of elasticity, thermal conductivity, all these are physical properties. Poisson's ratio, all these values I can find in the subpart 2. Okay, but right now our focus is to find the allowable stress that I can get where? In subpart 1. Okay, so in subpart 1, if I just expand it, you see there are lots of different tables available. Any reason for so many different tables, guys? If I have to find a stress value, there will be one material and there will be properties. Why there are so many tables? Because section 2 caters to lots of different codes. Apart from section 8 division 1, we are referring it for section 1, section 3, section 8 division 2, right? Section 4, lots of different design codes are there. For that, all of those design codes refer section 2 part D for the material properties. Okay, and also there are different types of materials like ferrous material, non-ferrous material. So when you open table 1A, you see that for which codes it is required. Like section 1, if I want the property of material and my design code is section 1, I need to refer table 1A. Apart from section 1, there are other codes also. In that, there is section 8 division 1 also. Okay, which is right now our focus. So section 8 division 1, if I have to find out the allowable stress as per this division for a material, let us say section SA 516 grade 70, I can refer this table. So in this table, you can see there are different composition. Okay, first of all, before composition, you can see that this is for ferrous material. So there are different tables for ferrous and non-ferrous. If you see 1B, 1B is applicable for same design codes, but it is applicable for non-ferrous material. Okay, so we rarely use non-ferrous for pressure vessel. So this is going to be our mainly the point of discussion, or this is the table which you are going to refer most of the time. So you can just remember it also. It's table 1A, which is there in subpart 1. Okay. Now we'll try to find out the property of 516 grade 70. So this is the specification number and grade. So I need to find out SA 516 material here. Okay. So if you see in the first page, you have specification and grade, some properties related to it. But there are following 3 pages which have some more properties related to it. Okay. So once I am not able to find the material in first page, I'll have to skip the following 3 pages and then again go to the page where again I can see these specifications. So again, I see the 515, 516 is also there, but grade 60 is there. I need grade 70. So I'll again skip these pages because this will have properties for the same material. Now I'm on this page again, 1A, same section. So if you go down, let us see 516 grade 65 up to 65. I'm there, but not 70. So 70 should be on the next page. So in this, okay, it's already highlighted for us. So SA 516 grade 70. So it is covered in serial number 33. Now we'll see what all the different properties which are listed here in section 2D and table 1A under stress value. So first one gives us the chemical composition. So 516 is a carbon steel material. Okay. And it will be always available in plate form. Okay. I cannot procure a pipe which is made from SA 516. It can be formed and made as a pipe. That is a different thing, but you won't be able to purchase it as a from mill as a starting point, okay, as a basic product form. So this is a plate form. This is the specification and grade. This is a UNS number, which is kind of Aadhaar number for a material. Through this, I can relate it with different other codes also. We'll not go into that detail. This is P number and group number. P number 1 and group number 1, 2 is related to welding property. So similar weldable materials are listed in a same group so that we can have a common welding procedure for all of them. Okay. So you can see here, all these materials which are listed here, all are in P number 1, some are in group 1 and some are in 2. So we can have a similar welding procedure for all of it. Okay, I don't need to find a different methodology for that. Now again, I will go to I could not find allowable stress here, okay, in first page. So I'll go to next page. Again, I'll start with same serial number. In 33, that 516 grade 70 is listed. So I'll go to the same serial number. There is minimum tensile strength given. So 516, you guys can note it down as having 485 as tensile strength. Okay, this is the minimum value which it should have to qualify as SA 516 grade 70. 260 is the yield strength, minimum yield strength for 516 grade 70 material. Okay, so you can write it down, 260 MPa as yield strength, 485 as tensile strength. Okay, but what we are looking is the allowable stress. Okay, like Keshav said, I need allowable stress, not any other property. So for that, I'll go to next page where you can see that allowable stress are listed based on different temperature. So again, I'll go to same serial number, which is 33. Okay, I can pick a stress value but I need a design temperature, right? For that, but I can see here we have not defined the design temperature. So I need that value also, right? What temperature you want to take, guys? Any value?
400.
400. Okay, let us start with 400 degrees Celsius. So once that design temperature is listed, first of all, we need to see whether the code permits that temperature for that material. Where I can see that? I can see it here in the first page itself. Okay, means the page where the property starts, so second page. So for 33 serial number, based on different design codes, which this table reflects. So for section 8 division 1, what is the maximum temperature limit for using this material. So you can see here for 516 grade 70, the temperature limit is 538. So I can use it, right? Guys?
Yes, sir.
If the same thing would have been happened and my design code would have been section 3, there it is permitted only up to 371. So I will not be able to use it. Making sense? But for section 8 division 1, it is permitted up to 538. So I can definitely use it. Okay. Now let us try to find out what is the allowable stress value. Okay. Now I'll find my temperature here, which is 400 degrees Celsius. Okay. For that temperature, if you come down, what is my allowable stress value? What is my allowable stress value?
101.
101 MPa. Okay. So I got the allowable stress value. What is the unit? It's in MPa. You can see that there. So allowable stress is 101 MPa for 400 degrees Celsius. There's one additional thing which I like to tell you guys. You might not be able to understand it very clearly, but at least you should know. Okay. You can see that. Do you find any difference in the way the values has been written? 123 and 101 specifically? Any difference you guys can find out in the way it has been written? Anyone of you?
As temperature increases, allowable stress is decreasing.
Yeah, that is a good observation. But the difference between
Major decrease.
yeah, the what I want to
The
say.
font style is changing.
Sorry, font size
Font
is,
style is changing.
is it or something else?
101 is written in italics form.
Yes, that is exactly. So 101 is written in italic while this is written in normal. So this is not a mistake. Okay. What code wants to imply that after this 375 degrees Celsius, when italic comes, that means there is a problem of creep. Creep can occur in my material. Okay. Now, what is creep? You can see in detail. You may not require at this stage, but if you're curious, you can definitely see that. So you have to perform a FEA to see whether the creep is becoming dangerous for you at that temperature or not. Okay. So that additional thing you have to do, but right now we are not going into that detail. So we'll just keep the allowable stress at 101 MPa. We have design temperature. Anything else you want, guys? Or this is enough data for us to design? Do I need anything other than this? Any one of you? Is it sufficient data? Yes, no?
Yes, sir.
Sufficient for design?
Sir, length.
Yes, we need vessel length, right? Or the length of the cylinder. So we'll not call it vessel. Right now we are just focusing on the cylinder. So we need the length of cylinder. Let us take it as 10 meter. Anything else? Corrosion allowance, right? We need corrosion allowance, right? So what value you want to take for corrosion allowance?
3 mm.
Normally for carbon steel, we take 3 mm. That is the standard value. So let us take as 3 mm. Anything else? Anything else apart from corrosion lance? There is a property related to welding of the cylinder, okay, which is called joint efficiency. Okay, because we are achieving or making the cylinder using a plate, so I need to weld it, right? So if I'm welding, how good I'm welding, that will definitely depend or may decide the failure, right? Yes, no?
Yes, sir.
Okay. We'll discuss about this joint efficiency and how it depends upon the radiography or other ND technique which you are doing. Okay. And based on that, this joint efficiency is considered. So if you are doing 100% radiography, that means you are checking the weld thoroughly. Okay. Radiography is a volumetric examination. It will check the full volume, full thickness which you are welding. If you do some surface examination like liquid penetration examination or magnetic particle examination, you can write down these things and you can just search these terminology, so it will give you a good idea, what technique we are talking about, so you will have better idea about these techniques. So liquid penetration examination, LPE. Okay, so you can just check how it is done, so it will give you a really great idea about how the surface examination are performed. MP is for magnetic particle examinations. It can be done only on ferrous because it's magnetic. It depends upon the magnetic property. So if I'm doing volumetric examination and checking the full thickness of the weld, okay, then I can say that my weld material is as strong as base material. So I'll take my joint efficiency as 1. Okay, this thing is very clearly defined in code. Okay, so we will see mostly in the code also, but right now we'll just assuming. So hope you got that idea. If my joint efficiency is 1, that means it is as good as base material. There is no problem, no defect in the weld. So it is as strong as base material. Okay, so now can we say that we have all the data related to the design, right? Now if I tell you to design, okay, what formula you are going to use? You have not studied code till now, so what formula you are going to use for calculating the thickness which can take care of this much pressure? Guys?
The circumference is, sir.
Yeah, rightly. Hope others also are. That is the reason we learned that circumferential and longitudinal stresses, right? This was the purpose for doing that. So now let us try to draw this. Okay, this is a cylinder which we are trying to design right now. Okay, so if we are making it from a plate, which we are doing, there will be weld joint. Okay, like this. If there are multiple shells, there will be circumferential joint also. Okay. But we know that the thickness is governed by the circumferential stress, which acts on the longitudinal seam. Okay, the direction of longitudinal stress is in the circumferential seam. Okay. And we know that the circumferential stress is twice more than the longitudinal. So we know that circumferential stress is more, so that is going to govern the thickness. So that will be my basis for thickness calculation. Okay, so you guys are in line what we just said, going into your head, able to visualize or confused?
No, sir, clear.
Clear, right? So I've just written the stress value which you take, right, in the PD by 2T. Same thing, T I have taken here because now S is the known thing and our job is to find out the thickness, right? So in this case, this is the formula I have to use. Clear to everyone? Guys, any clarification if you have, this is the time. Okay, because further than that, it will become more confusing if you don't understand up to this. So please be free to ask if you have any other query or any query up to here. All good, guys?
Yes.
Yes, sir.
Yeah. So if you want, you can just type in chat box also. Okay, that you have understood. Okay, so now if you have to find out the thickness with this formula, can you just calculate and tell me? I have written the formula. All the values are also there with you. Can you quickly calculate by using this formula and tell the thickness to me? Hope you guys are doing it.
So 247.5 mm.
Okay. 247.5 mm. Anyone else? This was by Hitesh, right?
Yes, sir.
So don't depend upon his value, guys. You can tell me.
Same, sir. 247.5 mm.
Okay, and this is
24.75 mm.
okay. Shashank, 24.7.
Yes, sir. Yes, sir.
Shashank got 24. So now we have a variation of 10 times. So what can be the where who is doing mistake here? Anyone getting some other value?
So 24.75.
Okay, so that was Mubasir.
Yes, sir.
Okay, anyone else?
So 24.75.
The same 24.75 mm.
Okay, one also 24.7. Everyone is getting this value. Okay, let us now calculate and see what is the right value. Okay, what should be my p value? Can I take directly 20?
No, sir.
No, sir.
Right, that is where I think Hitesh did the mistake, right? Hitesh, you took 20, right?
Yes, sir. 10:5.
See, 20.
There only I mistake.
Okay, see, 1 bar equals 0.1.
10:5.
We are trying to calculate in MPa. Why in MPa? Because it's Newton per mm square. Why we want mm? Because other dimension I'm going to take mm, right? You can see all the dimensions are in mm. So when you are doing calculation, try to do the calculation of the unit also. If you take in Pascal, you will be doing Newton per meter square. But if you are dividing that with mm, then you have to convert it, right? So you won't do mistake when you do the calculations of units also. Making sense, guys? Yes, no? So P
Yes, sir.
I'll multiply with 0.1 Okay. So now I have P. What is the D value? 2500. Yes, no.
Yes, sir.
Okay, right now let us take this. I'll come back to this again. PD divided by 2 into S value. Now you see that this also gives you indication that it's in MPa, right? So I need pressure also in MPa. And then it will be struck down. Making sense? What I got now? Why I got it like that? Because I didn't put the bracket. Okay. So we have 24.75. So this is the right answer. Slight modification in this due to diameter. Do you remember we studied that all the dimensions should be in corroded condition? Okay. So if the vessel is corroded, that time also it should be able to contain this 20 bar pressure, isn't it? Or you want it to fail when it is in corroded condition. It should be able to take the full 20 bar pressure even in corroded condition. So in corroded condition, what will be my dimension of diameter? What will become 2500 plus 2 times corrosion allowance. Yes, no?
Yes, sir.
Okay, I think we discussed this, right? Last time, that
Yes,
increasing
sir.
corrosion. So if you guys remember, then you won't find it difficult. So now instead of the diameter taking as D4, we'll take it as F. Okay. This is your right value. Okay. Making sense? Clear till now?
Yes, sir.
Great. Now this was the design method, we can say as 1, okay, which you will do right now, which being in college. Now, if you have studied a code or you're a design professional in working as static equipment design engineer, you will use design method 2, okay, which is based on ASME section 8 division 1. Okay, so if I use this, let us see how it is defined in code. We'll open division 1. We will go to UG 27, which talks about the thickness of shell under internal pressure, because here the pressure what we are considering is internal. We will learn about external pressure also, but right now the target is internal. So if you see the formula for circumferential stress, thickness is equal to PR divided by SE minus 0.6 P. Okay, so let us take this as it is, and then we'll just copy it, paste it here, and then we'll talk about it. So P, you know, right? P, there is no confusion. Now here we have R. What do we mean by R?
Radius.
Yeah. So radius, now whether it is inside radius or outside radius, how will come to know? So for that, we need to see the definition. So whenever code is defining, you know that code will define all the assumption which is just taking. So R is the inside radius of the shell. Okay. So now we know it's inside radius. So it will be half of your diameter. Making sense? Guys? Yes, no?
Yes, sir.
Yes,
Yes,
sir.
sir.
All other things already we have S value, joint efficiency, which we didn't use here, but we have noted it down. That is also there. So it is 1, so it is not going to make a difference. Then again 0.6p, which is addition. Okay. Now if I calculate the thickness, then my p value, which is 20 into 0.1 into r divided S is the allowable stress into E is the joint efficiency minus 0.6 times P is the pressure. Okay, pressure. Guys, can keep yourself muted. Okay, because we are hitting lots of noise. Yeah. So now I'll say enter. This is the value which we got. Okay. By bookish method, we got 24.8. By using asemi, we got 25. Okay, more than your bookish formula. We are going to see why and why this formula is different and what is exactly the difference. So now if you just try to relate these two formula, okay, PD by 2T or PD by 2S with this, okay, if I just write this formula also in this term, how I can write it? P will remain same. D I can write definitely as 0.5 times R. In R terms, I can write, sorry, 2R, sorry. Just a minute, guys. Yeah, sorry, it was a call. Okay, so we were talking about the relation in the formula. So D I can write as 2 times R, right? You guys can hear me, right?
Yes, sir.
Yes, sir.
P into TR, 2TR, then divided by 2T. I'm just writing the same formula and trying to make it similar to this one. Okay. So for that, I just D I have written as 2R, nothing more. So now I can definitely 2 and 2. No, those will be gone. So I can write as PR divided by T. Okay. So instead of T, we are keeping this side. We are trying to find out T, right? So there will be S instead of T. Is it making sense? Guys? Here I'll use S. Okay, because T is what we are trying to find out. So we can write it as PR divided by S. Now, is it looking a little bit similar to this? PR
Yes,
is
Yes,
common
sir.
now, divided by S. Now, E if we take as 1, okay, so E is also gone. So S, only the difference is that minus 0.6P, which is getting subtracted here, right? And if we take the pressure value, like for in our case 20 bar, which is 2 megapascal, that 0.6 time of P is nothing but what it will be, 0.6 time of 2 MPa, 1.2. Okay, compared to this from which we are subtracting is 138. Okay, so this is the difference, guys, 1.2 MPa. Okay, which is there at all and nothing else. Making sense?
Yes, sir.
Okay. Now, why this is there? For that, do you remember that when we calculated this formula, we assume that it's a thin shell. Okay. Thickness is very small compared to the diameter. That is the assumption for this theory. Okay. So normally it gives good approximation of the actual stress when it is a thin shell. When the shell becomes thicker, then it will start giving a value which is not exactly the same as what it will be there. Okay, little different value. It will not give a good result for thicker shells. Making sense? Because it's a thin shell theory. This is also thin shell theory, but it can go up to 0.5 R. If I open the code, you will be able to see it, which assumption it is making. Okay. So this formula holds good, okay, when thickness does not exceed 1/2 of the inside radius. Okay. So if the thickness exceed 1/2 of the inside radius, then it will not give you good result. Okay. You will have to use a different formula for thickness calculation. Do you know what we use for thick cells? Have you studied thick shell theory?
no, sir.
No, sir.
Which is also called Lame's equation. That is S is equal to P and multiplied with R outer radius square, square plus R. So this is not important, but just I'm writing it down. So in case you don't have to remember this. Okay, and then again, same thing in minus terms. Not divided, but again, I think it's divided. And here it is minus. Okay. So this is called Lame's equation. Okay. So if my shell is thick, okay, thick means if my thickness is more than half of the radius, in that case, this is the formula I need to use. Okay. there is a very interesting graph which is given in one of book I have shared with you. That will give you exactly what we are talking about. It's a very good book if you want to refer any book for whatever we are doing right now. Okay, this is the equation which I'm talking about. This is the graph. Okay, so now there are three different graphs given. Okay, this 2.3 graph is related to PD by 2T. Okay, equation 2.12, which is represented by this graph, it corresponds to Lame's equation, thick shell. So this is thick shell, this is thick shell, this is thin shell, and this is our ASME formula, which is shown in dotted. Okay, so by doing small modification in the formula, you can see it's matching with thin shell theory also, and where the thin shell theory cannot predict the stresses, actually there also it is able to. For thick shell it is very close to thick shell formula, okay, or for thin shell it is close to all. So it can give a very good stress if your thickness is less than half of the radius. Making sense, guys? Is it making sense?
Yes, sir.
So you don't have to use a Lame's equation or thin shell theory if you are doing a code design. Just if you are not able to meet this, that means you won't be able to give the stresses exactly. So you may have to go for either finite element analysis or may have to see a division 2 for the formula. Okay, but this will be a very rare opportunity because the thickness becoming half of the radius, the thickness has to be very large. Okay, so that pressure itself will go beyond whatever is permitted in section 8 division 1. Okay, so now you know the basis of why this modification is done, so that it is not derived but calculated based on experiments. The graph has been drawn, the values, actual stresses has been seen, and then this modification was done so that it will suit the different thicknesses. Even for the lower thicknesses it will give good result. Okay, that is the intention. Making sense, guys?
Yes, sir. Sir,
Yeah.
sir, the R value will be correlated or normal?
What we took?
Normal one, sir.
We took corroded, right?
No, sir. Corroded will be 1253 in the ASME method, sir.
Here you are saying?
Yes, sir.
We used, where is the radius? D19, 1250, correct. So here we'll have to add the corrosion lance. Always it has to be corroded. Okay. So if I'm using R, I need to add the corrosion lance. Very good. Ahmad, right?
Yes, sir. Thank you.
Good, Ahmad. So R, like we have already studied that all the formulas which we are going to study, they have to be in corroded condition. Okay. So this is the thickness which we will get as per code. Okay. This is based on circumferential stress formula. Now, do we need to calculate also based on longitudinal stress formula? Do I need to calculate?
So no, because it is only the half of it, so it will be less.
Yes, you're right. But then there can be other design loads. Right? This stage, I don't need to see the longitudinal, but if I'm doing a pressure vessel design where there are other loads also acting on the vessel, okay, and my vessel is tall, if the wind is acting, then again the longitudinal stresses are created. Okay, so in that case, it may get added to the longitudinal stress and may determine the thickness. Okay, so once you are doing code calculation, you have to perform all these, if and buts. So whatever is there, we have to perform. So now
So
can
if
we,
we perform
yeah,
the circumferential, if we take out the thickness from circumferential and longitudinal, the value will be different. So which one to consider? The greater one?
great. So if let us calculate what we get from longitudinal. I'll just paste it and then you guys can do the calculation. Okay, so this is the formula. So can you guys just calculate and tell me what thickness will be required for this?
Twelve 12.36.
12.36. Everybody is getting the same value.
And
So 12.357.
Okay, so that can be rounded to 36. Any other value? If everybody getting same, I think it's half of it. So it's okay. Now, this is the thickness required with circumferential stress, and this is for longitudinal. So what thickness I need to select?
Maximum.
Maximum. Can I select the minimum one?
also
What will happen if I select the minimum one?
Circumferential criteria will not
circumferential
be.
stress.
It will fail in circumferential stress, right? It will fail due to circumferential stress. So I cannot have a different thickness in circumferential and different in longitudinal, because finally the plate thickness is one, which I can select. So this 25.11, okay, which thickness we got. Now, do I need to add corrosion lines in this?
Yes, sir.
Yes, because this thickness is without any corrosion lines, right? I removed all the corrosion lines and then calculated the thickness. So now I need corrosion lines, right? Everyone is getting this? Because this is the portion where many gets confused. Why, if you are removing, someone may say that you're adding the corrosion lines in radius, then why again in thickness? Is it making sense, guys? Yes, no?
No, sir. So please explain it, why we are adding it again.
Yeah. So I was
Well,
waiting.
actually, in the code we have given that the dimensional symbols are what we are in corroded condition, right?
Correct.
So in the formula we are not using the corrosion allowance. So the value of R in the equation would be 1250.
Here.
Yes, sir.
Okay. So if you are not using corrosion, then it will be 1250.
Yes, sir. Because if the formula is in corroded condition, then we have to neglect that R out of the. We have to neglect the corrosion allowance value in that R.
Correct. That's what we did.
But sir, if we are adding 3
Okay. I think you missed the last class or what? You were there in the
No.
last class?
Yes, sir.
Okay. So I think you missed that point which covered this. So first of all, this is the very common confusion, and I have to explain this. So don't consider that it's a silly question or something like that, because this is the point where almost the professional also get confused. Okay. So is it clear to others, or all are confused?
No, sir.
Yeah, Hitesh, Ahmed.
Yes, sir.
I am getting doubts regarding this again and again.
Okay, great. So let us consider that everybody is having doubt here. Okay. Okay. See, that orange part here is the shell thickness which is going to be there. Blue part is your corrosion allowance. Okay, and black denotes the ID. Is this figure making sense?
Yes.
Yeah, this figure, I'm not asking whether I have answered the question. I'm just asking.
No, sir. Figure is making sense.
Making sense, right? So again, I'll explain. This blue color here indicates the corrosion allowance. Okay. Now, the confusion which all of you might have is what ID, first of all, I should take. 2500 or 2506. Okay. Okay. To answer that, now let us complete this and again we'll come back. Okay. Now design thickness, you got 28 mm. I'll come back. I'm trying to see from which point I need to explain. Guys, so do you get 28 mm plate, or I need to select a plate which is available in market?
Available in
standard size.
Standard size. So let us take, we got 30 mm as a standard size. Okay. Now I got 30 mm plate, formed it in this shape. Okay. Now analyze this. So when this is 30 mm, 3 mm is the corrosion allowance and 27 mm is the actual thickness. Making sense now?
Yes, sir.
Only the figure. I have not explained it completely. So I'm just asking about the figure. So this, when we talk about this figure, if I give it a value, then this blue color is 3 mm and the orange color is 27 mm in our case. Okay. Now, do I need 30 mm for design? What I need for design?
27 or 28.
Or 28 or 25. There are 3 thicknesses now. Which one is required as per design to take care of this pressure?
20
bar. Which one is required? 25 mm 20.
28 mm because corrosion allowance is added.
Okay, but why we don't want to add that, right?
So 25 mm.
25 mm. Okay, so let us see 25. Now let's take a different case. Okay, now let us take a case where there is no corrosion allowance added. Just forget about, let us consider that this is 1250. Okay, we have not added corrosion here also. Radius is also 1250. Okay, now the thickness which I got here is 25. Okay, let us round it off. I got exactly 25, and I got the 25 mm plate also in the market. Okay, now if it is confusing you, let us take 1250 itself. Okay, or let us make this as 0. So your radius is 1250 now. Okay, so I have 25 mm. I got 25 mm plate. Making sense? So once I got this plate, I have to form a cylinder, right? I am a fabricator, so I have designed it. Now I want to fabricate. So I have formed it in the form of shell. Okay, and what will be my diameter right now just after forming? 2500, right? My diameter will be 2500. Okay. I have formed it, welded it, okay, and then supplied to my client. Okay, painting and all whatever was required from outside, we did. We supplied it to client. Client has installed it in operation. Okay, when he installed and when operation starts happening, then the vessel starts corroded. Corroding started happen. Vessel started corroding. So my thickness will go down.
Yes, sir.
So if my thickness, like even after 1 month, is it corroded to 24. Now, can I say that it is safe as per my design? Because my design thickness was 25 mm, right? So immediately it will be rejected. Again, after 3 months, I'll have to make a new vessel because now the design is not passing, right? Making sense?
Yes, sir.
Now, what we do, so this is a problem, right? We have not considered any corrosion allowance. Okay. Now let us see what we do when we design as per code, then what we do. Okay. Now I have added 3 mm as a corrosion allowance. So while designing, what I'm trying to do is that I have to design for end condition. Means this vessel I have designed for 10 years, right? Because client will need some years of operation, isn't it? Guys?
Yes.
Yeah. So I have designed it for 10 years, and in 10 years, the corrosion is assumed to be happen. Okay, it is expected to happen, and that value is 3 mm. Okay, that client has given us that last time when I had the same operation, it almost in 10 years it corroded 2.5 mm. So I need you to take 3 mm as corrosion allowance and design this cylinder for me. So when he says that, is he violating the requirement of code? Code says you don't have to consider corrosion allowance. Guys, when client is saying take this 3 mm as a corrosion allowance and design this cylinder, is he telling us to violate the code?
No.
Then how we should compile his requirement? See, what client is saying that I know that whatever vessel you are going to give me, the 3 mm, which is this blue color, is going to be corroded. So whatever is remaining, now my vessel will look like this after 10 years. So whatever is remaining, it should be able to take the 20 bar pressure, okay, and whatever temperature and other design parameters we have given, it should be able to take, right? Making sense?
Yes. Yes.
So when the vessel is corroded, which is going to happen, still it should be able to, it should have a thickness which is equal to the design thickness, which I need minimum thickness to take care of this pressure, 20 bar, right? Because vessel should not fail, right? After corrosion, knowing that 3 mm is going to corrode. So I have to design for end of life, right? If I design for start of life, then we know that we are going to fail, isn't it? Is it making sense, guys?
Yes, sir. Understood.
All of you? Aman,
Yes, sir.
Clan. Yeah, making sense? So when code is saying that you have to consider corroded condition, this is what code wants to say. Don't consider when the vessel is new. When it is new, it is going to take a lot more pressure than what you have designed for. But it has to run for 10 years in operation, and there it is going to corrode. The thickness is going to go down. Your dia will increase by that much. In that case, also, you should be able to retain this pressure. Okay, you cannot say that, why corrosion is happening. Client has already told you that 3 mm is the corrosion allowance. It is going to happen. So you have to take care of that in design. Okay. Making sense?
Yes, sir.
Yeah. So now when we take the radius, knowing that when my vessel is new, that time it will be 1250. The radius will be 1250 when it is new. When it is corroded, that time what will be the thickness? 1253, right? Is it making sense now? See, I might be explaining too much, but because I'm not getting the required response. But the intention is that you have to understand this point. This is the basis for all the design actually. Is it making sense, guys?
Yes, sir. Yes.
Yes, sir.
Yeah.
Yes, sir.
Yeah.
Yes, sir.
Great. Good. Still, if you have any confusion, try to think of it. Now you know what is the normal procedure. So if everybody is doing that, so there must be something which you are missing. So try to think again with the same process. You will be able to understand. Okay, that's what we are trying to do here. So we took now 30 mm as a, so this 28 mm, which is after adding the corrosion allowance, this is called design thickness. Okay, this is 25 mm which we got. This is the minimum thickness. So this, even after corrosion, this should not go down because this is the minimum thickness required to take care of this pressure. So if it is going below, then it is a dangerous thing. It may fail. So it should never go below 25. I'm adding 3 mm as a corrosion allowance, knowing that after 10 years, it will become 25. So I took design thickness as 28. Now, when I started searching for this plate in market, I got the nominal thickness of the plate, which I could find in the market is 30 mm. So I'll take 30 mm as a nominal thickness, form the cylinder using this 30 mm plate. And the dia at that time will be 2500. Okay, so when it start corroding, my diameter is going to decrease. And that is the reason we are designing this with all these values. Hope it is making sense now.
Yes, sir.
Yeah. Okay. Now anybody can find out with this nominal thickness how much pressure my vessel can take, whether it will take the same pressure 20 bar or it can take more than 20 bar. Can you find out?
Yes.
Yes, sir.
Which we can call it as maximum pressure which it can allow by using the same formula. Okay, you can find out T is known now. Okay, you have to find the P value.
So now it can take 23.84 bar.
23.84 bar. Okay. All of you getting the same value? I'll just modify new. I have already told that it's new condition. So you have to take 30 mm as a thickness. I'll write one more thing, new and cold. When my vessel is in cold condition, means if it is at room temperature, then how much pressure it will be able to take? What will change if I say that? New, you have already selected 30 mm. For cold, what you will do? So this 101 MPa is at 400 degrees Celsius. When I say I need this at cold, that means I want this allowable stress at room temperature. What will be this allowable stress at room temperature? I'll go back in section 2. Part D, we have already opened it. So instead of 400, I'll find it at 40 degrees Celsius, so which is 138. So I have the 138 MPa value, and this is what I will use in this equation. Yep. Now tell me what is your pressure value?
So 32.57 bar.
32.57. Yes. Anyone else?
Sir, I'm getting 23.83.
23.8.
Sir, 32.
Sir, for the previous condition.
So I'm talking about maximum pressure in new condition and in cold. So
So at cold it is 32.57.
32.57, right? Everybody is getting that? 32.5?
Yes, sir.
Okay,
Yes,
you
sir, 32.5.
just have to put S value as 138, T as 30. Okay, all others are already which we have calculated. Okay, so 32.57 bar. This we call maximum allowable pressure. And in small we write NC, new and cold. This is the code term. Okay, maximum allowable pressure when my vessel is new and it is cold. Cold means at room temperature. So this is the maximum capability for which we have designed it when my cylinder is new. Okay, so we started with 20 bar, but finally we have designed for 32.57 bar. Okay, now there is one more term which is called MAWP. Okay, this is calculated in hot and corroded condition. Now, can you tell me this value? First of all, what are the values? Like what will be the temperature first of all, for which allowable stress you will take?
400.
400, right? Because we are talking about hot. So hot means design. So S value you'll have to take 101. Okay. And then corroded condition. So the thickness which you took 30 is new condition, right? When it will corrode, what will be your thickness? In corroded state, what will be your thickness?
27.
27, right? So 30 minus your corrosion allowance, 27 mm. So now just find again this MAWP.
So 21.48 bars.
21.48. Anyone else? Everybody is getting this 21.48.
Yes, sir.
Yeah. Okay, so now we have three different design pressure values. Non-design pressure values. So we started with 20 bar. Okay, in hot and corroded condition, my vessel can take 21.48. It has to be more than this design, right? So that means when it is at the end of its life, then also it will be able to take more than what it is designed for. And that is the requirement, isn't it? Making sense?
Yes, sir.
Yes, sir.
When it is new, definitely it can take much more. Okay, because strength is also good, thickness is also more. So it can take much more pressure when it is new. Okay, making sense?
Yes, sir.
Yeah. So got something new, whether it was exciting, guys, whatever we covered till now, today's class.
sir.
Yes, sir.
Yes, sir.
Yeah, great. So if you follow this procedure, this is how industry will design. You can make a cylinder and supply to anyone. Okay, this will be as per code. Nobody can question your design. Okay, so you have learned today how we design a cylinder for a pressure industry. Okay, and that is definitely great. Okay, we have understood all the intricacies also, that where the most of the people will find a problem. Even if you ask some professional who is already doing, he may also miss this adding of the corrosion allowance and may get confused in taking whether we should add or subtract, what should be my starting radius. Okay, so really good that you could understand. Okay, and now I'll give you one homework. All of you having this code, right? I have shared this code with you. You guys have that, right?
Yes, sir.
Yes, sir.
So now I'll tell you to, as a homework, find out thickness for a spherical shell. So what you have to refer, UG 27D. If instead of cylindrical, if you have to design a spherical shell, what will be your thickness? Okay. And also for the Deschamps. Deschamps means if you have a elliptical head or a torus spherical head or a hemispherical head. So just try it, any one of it also, it's okay. So if you have an elliptical head attached to your cylinder, then how to calculate the thickness for internal pressure? Okay, right now we are only concerned about internal. So the cylinder which we have designed right now, it's good for internal. We have not designed it still for external pressure. That still has to be seen. We'll have to see what external pressure is given as an input, and then we'll design this. Okay.
सर ये MAPNC क्या है?
MAPNC. Hello.
Yes, sir.
Yeah, Ahmed, you are asking?
Yes, sir.
What is the question?
Yes, sir. ये क्या है?
MAPNC क्या है? वही तो हम लोग अभी तक एक्सप्लेन कर रहे थे. You would like to explain to Ahmed what it is?
Maximum allowable pressure, new and cold.
So see this, don't go in what we are writing here. It's a pressure which my cylinder can take when it is completely new. Okay, just we have made this and at room temperature. It is at room temperature. It is not at operating. That time, what is the maximum pressure which it can take?
सर वो अगर न्यूली मेड है तो उसका इनसाइड रेडियस 1250 रहेगा ना?
Sorry?
जब वो न्यूली मेड रहेगा, अभी बनाया, तो उसका इनसाइड रेडियस 1250 रहेगा ना?
Yes.
वही इधर वैल्यू चेंज हो रही है.
1250 ही लेना है. यहाँ पे आप क्या लिया है? जो
सर ये 1253 से ये वैल्यू आएगा. अगर 1250 लेंगे तो वैल्यू चेंज होगी.
वेरी गुड पॉइंट अहमद. अहमद कोरोजन के मामले में बहुत सटीक है. ग्रेट. So if you guys have calculated this as a
32.649 hours.
So whoever has calculated, you can just check that. So see, this is new, right? So you have to take this radius which is in new condition. This is diameter in new condition. So half of that 1250 will be the radius. Clear है ना सबको?
No, sir.
Yes, sir.
Yes, sir. अब हो गया.
Yes, sir.
किसने नो कहा? So don't worry about Ninad, right?
Yes, sir.
But क्या clear नहीं हुआ? Ninad?
Yes, sir.
नहीं मतलब क्या clear नहीं?
1253 के जगह पे 1250 क्यों लिया जब न्यू है तो? क्योंकि कोरिजन अलाउंस तभी तो यूज करेंगे ना.
यूज तो करेंगे ही. जब आपने वेसल को डायमीटर जब नए में बनाओगे तो कितना बनाओगे डायमीटर?
2500.
2500 डायमीटर बनाओगे तो रेडियस 1250 आ जाएगा. ठीक है. तो हम लोग कोरोजन का बात ही नहीं कर रहे हैं. हम लोग अभी जस्ट अपने रेफरेंस के लिए निकाल रहे हैं कि जब मैंने अभी सिलेंडर बनाया है, कोरोजन होने के बाद तो ये निकाला है ना हमने हॉट एंड कोरोडेड में. यहाँ पे जो आप रेडियस लोगे वो 1253 होगी सेकेंड वाले केस में. यहाँ पे 1253 होगी. यहाँ पे, क्योंकि ये न्यू के केस में हम लोग निकाल ही रहे हैं, केस ही हमने वैसा लिया है, राइट। केस हमने लिया है जिसमें वो बिल्कुल नया है, तो जो ये हम लोग अपने रेफरेंस के लिए निकाल रहे हैं। कैसे कहाँ यूज करना है वो मैं बताऊंगा आपको, क्यों निकाल रहे हैं, डेफिनेटली कुछ तो रीजन होगा ना निकालने का, तो वो मैं बताऊंगा आपको। बट फिलहाल आप ये समझिए कि फॉर आवर रेफरेंस वी आर ट्राइंग टू जस्ट फाइंड आउट, और हमने केस ही ऐसा लिया है कि कोल्ड है और एकदम नया है। तो नया है तो जो भी डायमीटर आपने बनाया है वही रहेगा, राइट। क्लियर है सबको?
राइट सर, यस सर।
राइट निनाद? Okay, clear to everyone. So now I think you will not get confused with what radius I should take. So कौन सा केस है वो देखो, वेदर कोरोडेड का है तो कोरोडेड लो। जब भी कुछ कोड का डिजाइन कर रहे हो तो you have to take always the corroded value. Okay, this which we did, it's not mentioned in code. Okay, this is mentioned in code to how to calculate MAWP. But why we are calculating this? This will come when we see hydro test pressure requirement. Okay, so अगर आपको ये नहीं भी समझा, then also it's okay. So for all these other things, you have to use the corroded condition. Making sense now?
Yes, sir.
Yes.
Great. So we'll close it here, and I hope you know what homework I've given.
Yes, sir.
Calculation of
Sir, can I leave?
hello.
Sir, can I leave?
Yeah, why not? You can leave anytime, yeah. See, anyone want to leave, definitely can leave. No, I'm not saying you to attend all the time. Okay. So anyway, we are going to close it. I just want to mention the homework. So a spherical shell thickness you have to calculate, and elliptical head thickness you have to calculate. Okay, this is the two homeworks. Okay, now you can go and enjoy your whatever Sunday is left. Okay.
Thank you, sir.
Yes, sir. Thank you.
Bye. Bye.
Thank you.
Okay.
Thank you, sir.
Bye.